Welcome, this is Information Service Engineering, lecture number 2, Natural Language Processing Part 2. This is the last part of this lecture. And in this part of the lecture, we will show you how to implement part-of-speech tagging. So you remember from the last part of the lecture, to do part-of-speech tagging, or shortly POS tagging, what you need is a set of tags and you need some raw text. And then you need a POS tagger, which combines both and produces a so-called tagged text, where all the words in the text, they are labeled or tagged with some kind of part-of-speech tag, which denotes the function of the word or the class of the word. Okay, so for an implementation of that, we have to think about a baseline, and then of course about an algorithm which somehow should be able to surpass this kind of baseline. So first we have learned that there are some unambiguous words which have a correct label, which means there are some words which only have one tag. So first of all, let's take the text, look up in the dictionary where are these unambiguous words that only have one tag and tag them with their correct label. That's the first step we do. And then we end up with a bunch of ambiguous labels. What do we do with them? So ambiguous words we could probably tag with their most frequently used label, which means we do, of course, some kind of language modeling. So we analyze a larger corpus, and then we try to find out which kind of tags are most often used together with these words. So this would be the second step. Then we have taken care about all unambiguous words and we have taken care about all ambiguous words. Probably there might be something left which is not in our dictionary. So what do we do with the unknown words? Okay, we can say, yeah, we don't know the word, probably it's a noun, which in some percentage of all of the cases is correct. So going the approach through in these 3 steps will build our baseline. The question now is, what's the quality that we can achieve with exactly this kind of baseline? And you might be surprised that this simple method already gives you an accuracy of 90%, so only 10% of error. So this is really high. So this is the bottom line, the baseline that we want to beat. What's the upper limit? How good can it be? So let's have a look. Today's state-of-the-art POS tagger, they achieve about 97% of accuracy. So it's only 7%, between 90 and 97, what technology is able to accomplish. But you should also keep in mind that also humans are not really perfect, because sometimes, in ambiguous cases, also humans do not agree about a decision for a POS tag. So humans, and this is the ceiling, perform also only around 97% accuracy. So this is the range we deal with, between 90 and 97% that we want to achieve with some kind of sophisticated approach. So what can we do? What approaches are available to do more sophisticated POS tagging? Let's have an example. We have here time flies like an arrow. So let's have a look. Time, yeah, of course it could be a noun. It could also be a verb. Flies looks like a verb, but could also be a noun in plural form, of course. Like, as you see, like here can be many different things, starting from a verb, going over a conjunction, and so on and so on. So there are lots of possibilities. And a simple, this is a determiner, so this is unambiguous. And then you have arrow, and arrow also could be a noun, and likewise a verb. So since there is ambiguity in a sentence like that, we cannot simply do a dictionary lookup. We know that already. So the correct approach would be, or should serve in a way that from all these potential candidates, the correct ones are selected. And we have to find out what are the reasons or what are the cues that we can use to distinguish or to decide which one is the correct label. Okay, what kind of algorithms exist? First of all, there are so-called rule-based POS tagging algorithms. They usually come in a 2-step approach. It works in the following way. First of all, you use your dictionary and assign a list of all potential tags to all of the words. So this is something we already did in the previous example. And then what you do is you have handwritten or manually authored rules to restrict to a specific POS tag. So for example, that you say after a determiner, then most likely there is an adjective to come or there is a noun to follow. So this would be a handcrafted rule. This might work very well, but of course there might come situations that you haven't thought of, and then you don't know what kind of rule to apply and whether this fits or not. Another possibility is a probabilistic approach or a stochastic approach. It's probabilistic tagging. And this is based on so-called hidden Markov models, and this is something we want to go deeper into it afterwards. So this is an approach we want to follow, the stochastic approach, which means, again, we have to take care of a large corpus of already existing labeled data where we can look up probabilities. What is the most likely tag to follow after a word? So this is then stochastic. And then there are so-called transformation-based tagging approaches, and they take into account both approaches, rule-based as well as stochastic. So they combine both approaches together. And also there is the possibility to learn these kind of rules already from existing data. Okay, but now let's focus on the most popular approach, which is the stochastic approach. The stochastic approach asks what is the most likely sequence of tags for a given sequence of words. So the input is a sequence of words, your sentence, and you have to issue for that also a sequence of tags. And since this is probabilistic, you try to find out what is the most likely sequence. So the sequence that for similar or the same words has been used in the past most frequently. Okay, to give you an idea how this works, let's have a look at an example in a language that we don't understand. But nevertheless, we have the POS tags. So this is more or less also the situation that our computer is focusing or facing. So what you see here is words. We have no idea what the words mean. But nevertheless, in a tagged corpus, you already have the tags available. What can we see here? So you see here, for example, each of these sentences, and let's assume that each line here, followed by a period in the end or something in the end, might constitute a sentence. So you see each of these sentences starts with a determiner. So this kind of sequence that you see here might be a determiner. After the determiner, you see most times a noun. That's interesting. And in the last case, you see an adjective followed by a noun. The noun then in the first three examples is followed by a verb, and so on and so on. So what you look at it is simply, what is the most likely sequence? And of course you also look at the words. So you see, for example, that here many of the words, so in the first three sentences, the verbs that you see here, they are somehow the same. They are this strange 0 encircled and the 10 encircled. We have no idea what it means, but we see this is a verb and this is 3 times the same verb. And if the verb is used, then before that verb there was a determiner and a noun. So this already gives you an example or a feeling of the likelihood which sequences of word might evoke a specific sequence of tags. Now the question that we have to answer, or that our system has to answer, now we have a new sequence of words. What's the most likely tag sequence for that word? What do you think? Well, we see that it starts with exactly the same kind of word that also the other sentences start. So it's most probable that this might be a determiner. Wouldn't it be? Yeah. And we see also from the previous examples, last line, that the second word here, it's exactly the same like the second word that we have here in our new example. And in both cases, we have a determiner and then this word. So it's most likely that this also might be an adjective, which then is followed, although if we might not know the subsequent word, that this is a noun. So you see, by playing with the likelihood, or by playing here with the probabilistic likelihood, we are able to assign POS tags to a kind of language that we even don't know, simply from purely probabilistic observations. So to clear it up, I have here substituted the words that we don't know, again with words from the English language, and you see here the new sentence means a happy cat was singing, which means A, of course a determiner, happy, yeah, it's an adjective, cat, okay, it's a noun. So you see this is somehow the way how it is working. The only thing now is we have, of course, to bring this probabilistic approach into, of course, a formal form that we can implement on a computer. So the question is, how do we predict these tags? From our previous example, we have already found out that, of course, existing relations between words and tags are somehow meaningful. So, for example, dog is a noun, fox is a noun, A is a determiner, the is a determiner. So this is important. So these are words where only, of course, or most cases, the POS tag only depends on the word. But on the other hand, we also found out that relations between subsequent tags are important. So for example, a determiner is always followed by a noun or it's followed by an adjective and a noun. So we look at these two different kind of sequences and probabilities that are connected with these sequences. And by doing this probabilistically, we will find out that some of these POS tag sequences are much more likely to occur than others. You can see this easily with the Google Ngrams viewer. Here is a simple example. You see here 3 lines, a red one, a green one, and a blue one. And it's looking at the Google Book corpus, which is rather huge. And it looks for combinations like adjectives followed by a noun, adverb followed by a verb, or adverb followed by a noun. And you see here that the sequence adverb followed by a noun is much less likely than the sequence adjective followed by a noun over the entire corpus. And exactly this kind of probability we will use for the POS tagging approach, for the probabilistic POS tagging approach. The question now is, how do we resolve tag ambiguity? What kind of cues, what kind of features can we use for that? So our current observation could be we look at the word itself. So what is the word? Do we find it in a dictionary or somewhere else? Then we also can try to analyze the word. How is it composed? So what are the morphemes? What is prefix, suffix? What is the stem of the word? Then, of course, we can look at it. It's written lowercase or is it written uppercase to decide what kind of POS tag it might be. On the other hand, we can also take into account the word shape. So are there dashes or hyphens used or whatever? And then we have some surrounding observations where we take into account the context of a word, which means we can have a look at the previous word and also at the subsequent word. And also we can look at previous decisions. So what tags have already occurred in the sequence? So what is tag -1 and tag -2, for example? These are all observations that we can use, or features that we can use to base our decision which tag to assign to. So you see, there is lots of stuff where we can learn from. We will base our approach on so-called hidden Markov models. Hidden Markov models are really a nice tool that enables us exactly to cope with the problems like we have here. So what we want to decide is we want to find the best fitting sequence of tags that corresponds to a sequence of observations we made. What do we mean by observation? Observation, of course, is the sentence we get. You see here, you have a sentence consisting of single words. She promised to back the bill. 6 words. And of course, we want to derive a tag sequence. You see here 6 tags, starting with a pronoun, followed by a verb, which is in the past tense, and so on and so on. So you have a tag sequence that should be derived from an observation sequence, from a word sequence. This exactly we want to achieve based on the hidden Markov model. So now we have to take our probabilistic glasses and then, of course, try to look at it from a probabilistic or stochastic angle. What we do is we try to choose the tag sequence from this entire universe of possible tag sequences which is most probable given the observation sequence. So in formal letters, it's written in the way you are looking for a tag sequence. This is here T with a hat from 1 to n. And we want to maximize this argument, this T sequence, or select the appropriate tag sequence which maximizes the probability that the sequence occurs for a given observation. So T 1 to n occurs under the observation W1 to n. So the words 1 to n occur, and therefore we choose the tag sequence T1 to n, and we want to choose exactly the one that maximizes this probability. How do we compute that? Okay, this is some kind of conditional probability, therefore we are using the Bayes rule that you already know. So again, we want to distinguish what is T hat. For that, we apply the Bayes rule. What does the Bayes rule say? The Bayes rule says if we want to determine the probability that A occurs under the presumption that B has already occurred, this is equal to the product based on the probability that B occurs under the assumption that A has already occurred, multiplied with the probability that A occurs at all, divided by the probability that B occurs at all. This is the Bayes rule. And this somehow gives you always the connection between these two conditional probabilities, either A under the condition of B or B under the condition of A. Now let's try to transfer this to exactly our problem that we have. We want to distinguish compute the probability of the occurrence of the tag sequence T1 to n under the assumption that the following words W1 to n have occurred. And this, according to the Bayes rule, equals to the product of the probability that a word sequence occurs on the basis of a given tag sequence time the precondition that exactly this tag sequence really occurs, divided by the probability that the word sequence has occurred. So, what we want to do here is, in the end, we say we want to maximize the probability, and then we insert accordingly to the Bayes rules the following terms. So instead of simply writing P, the probability that the tag sequence 1 to n occurs under the assumption that the word sequence has occurred, we substitute this here by the other end and write we want to maximize the occurrence of the word sequence under the assumption that the tag sequence has occurred times the probability that this tag sequence really occurs. The interesting thing is we have to, of course, or we might get rid of the denominator, since the denominator for it's always the same. And if we try to maximize the probability, it's always the same denominator. So the point is, so we can get rid of it. It's the same result. And you see here, this one is the likelihood of the word string, and the other one here is the prior probability of the tag sequence. Okay, this now simplifies our problem, but on the other hand, we'd have to take into account an entire sequence of length n, which might be more or less complicated. And this is again where the Markov assumption comes into place. You remember the Markov assumption? Instead of taking into account the entire sequence, we only take into account the most recent past that occurred. You know, like in these bigrams, for example, that we have studied. So, what we can say, we can approximate the probability that the word sequence W occurs under the condition that the tag sequence has occurred. This can be approximated by the product that consists of the probability that a specific word in that sequence occurs under the assumption that a specific tag occurs with that word. And this, of course, you do for all words. So starting from the index I equals 1 to n. Which means this only depends, so the probably only depends on its POS tag, independent of the other words. And then you look at the tag sequences for determining the probability of the tag sequence. So what you do here, you say the probability of the tag sequence is approximated by the product of all tag sequences consisting only of the tag and its predecessor. So it's the occurrence of the tag t sub I under the assumption that t sub I minus 1 has already occurred. So you're only looking for the bigram. So this here is the typical Markov assumption. And then if you take these two approximations together to maximize again, or to determine the most probable tag sequence, you maximize the product that you get here from the single conditional probabilities that a specific word occurs together with a specific tag and that a specific tag occurs after a given tag. So these are two different kind of probabilities. First of all, this is the so-called emission probability for a word occurring together with a specific tag, and the other one is the transition probability, which means this is the probability going from one tag to the next tag. So what is the next tag in the sequence? What is most likely? This makes a so-called hidden Markov model that you see here in a very nice illustration. So here, for example, you see in the notes we have given the tags, and then you have arcs between subsequent tags which might occur, and there is of course a transition probability between the single tags. This is denoted in red color here. So the probability that after a determiner there follows an adjective is 0.7 or 70%, and the probability that after a determiner there comes a noun, this is 30%. From where do you get these probabilities? You get them from a language model. So you analyze a huge corpus and simply look at the tag sequences in there. On the other hand, you have these so-called emission probabilities, which means you have here probabilities. Given that you have a specific determiner, what's the likelihood that a specific word occurs together with that determiner? So let's have a look, for example, at the determiner. There you have the probabilities that the determiner is the particle the with 50%, or it's the undetermined particle a. This is 0.2, which means 20%. Every or some or no come up with 10% likelihood. And this is the way how you model your entire language. And then based on that, of course, you can do this estimation where you try to maximize the probability of a specific tag sequence for an occurring word sequence. So this is the way how, via hidden Markov models, POS tags are assigned to a sequence of words. It's as easy as that. Okay, so now we hope you have had a first glimpse on all the topics that are available in natural language processing. You know a little bit about how language modeling based on n-grams is working, how finite state automatons work together, or for example for morphological analysis, and also how part of speech tagging is working. Of course, this is not the entire subject natural language processing. There are lectures covering much more, but in terms of information service engineering, this is a good start to become familiar with natural language processing. So in the next lecture, we will continue information service engineering, and then we will talk about linked data engineering.